Okay, let's go. So what did we talk about last time? Let's review. Last time. So we learned a bunch of vocabulary, right? So this is the new vocabulary. Well, what's a hypothesis?
A proposition that can be either true or false.
A proposition, yes, something that's true or false. So a proposition, in other words, just a statement that is true or false. This coin is fair, this drug helps, this drug doesn't help. The null hypothesis. I wanted to talk about that Nature article. All right, we'll talk about the Nature article in a second. The null hypothesis is what? What's currently held as true or something you're trying to disprove. It's the defendant, right? We're not trying to determine whether the defendant is innocent. We're trying to prove that the defendant is guilty. We want to reject the null hypothesis. So something that we want to reject. That's why it's null, right? We want to reject if we can. We do not want to accept the null hypothesis. We can fail to reject the null hypothesis. We'll call that accepting the null, reluctantly accepting the null hypothesis. All right? And for some reason, this is, all right, let me get through the vocabulary and then we'll look at this Nature article. How many people read it? A handful of you guys? Isn't it amazing what's in there? All right, let's finish the vocabulary, one thing at a time. Alternative hypothesis. What's the alternative hypothesis? If the null hypothesis is innocent, it's what you're trying to prove, right? It's the guilt that we're trying to establish. So this is guilty. Guilty. We want to reject the innocence of the null hypothesis. We want to show guilt. We could make a mistake. We could let a innocent man go to jail. We could let a guilty man go free. Obviously, we want, which one did I say first? The former rather than the latter, or the other way around. We don't want innocent people in jail. So there are errors, inevitable errors. The probability of making a type 1 error is called Excise, or the level of significance. This really feels like the worst one, right? Because we said the guy's guilty. We accepted the alternative hypothesis when really he isn't. So this is the type 1 error is when the null hypothesis is rejected but true. Okay? And I'm writing it like this, but it's not that there's a probability of it being true. It's the probability that it's rejected, assuming that it is true. Okay, so some people write, it's the probability that, oh yeah, I didn't say what a critical region is, so let's remember what a critical region is. So C is a subset of all the possible outcomes, so this is all outcomes of our n experiments, is the critical region. What's the critical region? What's the definition of the critical region? Ernest?
Probability that you reject.
It's not the probability, it's the actual set.
Yeah.
The set of outcomes, so this is the set of all possible outcomes of our n independent samples, or maybe they're not independent or whatever, of our samples. The critical region is where we reject. It's the set of outcomes is the critical region where H0 is rejected. Right? So when we're creating a statistical test, we have three things to determine. What is our null hypothesis? What is our alternative hypothesis? And what are we going to test? What is the critical region? Those are the three things you input. Then you can calculate from those things what the size, or the level of significance of the test is, and the power that we're getting to in a second. If it's rejected, that means we saw the critical region. We're inside the critical region. So this is the probability of the critical region given that H0 is true. It's just another bit of notation. Somebody asked, maybe Ernest asked after class, what do I mean by the probability that theta is equal to 0.6? I don't mean the probability that theta is equal. There's no distribution on theta. I'm saying the probability that we saw 14 out of 20 coin flips given that theta is 0.6. Right? Just making that distinction. So is it clear what I mean by this? This is what we were doing last time? Great. And then beta is the probability of a type 2 error. This is, we let a guilty guy go. Right? So H naught is in fact false, or we accepted, so this is the probability that H naught was accepted. Again, I don't like that term, but that's historically what's used. Accepted meaning not rejected, but H1 is false. And it's not always that we're measuring that H1 is false, we're testing it against. As stated, there's no H1 here. Sorry, it's not always that H0 is false. We're not going to test necessarily the falsity of H0, we're going to test H1 as the alternative. So this is what you might think it should be, and in fact, it's just that. That's the purpose of the alternative hypothesis, to give us some distance potentially between the null hypothesis and the alternative hypothesis. So again, this is the probability that we're in the complement. H naught is not rejected. We're in the complement of the critical region, given that H1 is true. Okay? Yes?
I know you said that H1 doesn't have to be like the direct opposite of H0, so what, like, are there ever, so then wouldn't that mean that for some of them there's this weird space where like H1 is not true and H0 is also not true?
Yes. So for example, so this is a great question. Taylor had a great question. Okay? Let's look back at our example from last time. Which was H0 is the test that theta is equal to 0.9. We're flipping a bunch of coins or testing drugs or whatever. Our critical region was at least, so we had a number of coin flips. So we had a binomial distribution out of 20. And we said if at least 15 of them, if at most 14 of them come out heads, we will reject the null hypothesis. That was our critical region, right? 14 out of 20, out of n equals 20. And we'll reject that in favor of the alternative hypothesis, which was theta was 0.6. I'm just reminding you of the example we had last time. Okay? Certainly theta does not have to be either 0.6 or 0.9. It could be 0.7, it could be 0.4. Could be 8, it could be 1, it could be anything, right? So the quality of a statistical test depends, but this is, I've given you all the information. I've given you a critical region, what outcomes, under what outcome will I fail to reject or yes reject the null hypothesis in favor of the alternative hypothesis. So those are the three inputs to a statistical test. Now we have to say, is this a good statistical test? When I've rejected H0 in favor of H1, because this did not happen, we're in the complement of the null hypothesis, what was the probability of that kind of error? Does that make sense? So you're absolutely right. There's a whole range of other possibilities. And in fact, that's another word I needed to put up, simple versus composite. So another little bit definition, a simple versus a composite hypothesis. What's a simple hypothesis? Do you remember this bit of terminology? Simple means you completely determine the probability distribution. So simple completely determines the density function, PDF, of the sample. Composite does not. No. So for example, let's give an example. You have normal variables. Your sample is IID normal. And you're going to test, your hypothesis is that mu is equal to mu 0. Is this hypothesis simple or composite?
Composite.
Zach says composite. It's got to be composite, right, Mohammed? Why?
Because Zach said it.
Because what?
Zach said it.
Because Zach said it? That is a good statistical test. In this case, it's accurate. In a lot of cases, it's accurate. There are two pieces of information you need to know to determine what the actual distribution is. Normal is just a shape, right? Normal is determined by two pieces of information, the mean and the variance, or the standard deviation, right? This hypothesis is only testing the mean. So if the hypothesis is true, it says nothing about the variance. So this is a composite hypothesis. This is composite. Not. So this is composite. Okay? And one of your homework problems is, here's 10 hypotheses. Which of these are composite? Which of these are simple? How about this hypothesis? Simple or yes? Tell me again. A mono. Mona.
What does that say? It says mu equals mu naught.
Mu equals mu naught. So if I'm going to say the mean is 0, or the mean is 10, whatever I'm trying to determine whether the mean is, I have not determined the entire density function. I've just told you where the mean is, but not what the exact PDF, because I need the standard deviation. As opposed to a coin flip, a Bernoulli trial, where there's only one parameter, and if I say theta equals 0.9, now I've completely determined what that density function looks like. So this is a simple hypothesis. What if I put here theta is less than or equal to 0.6? Clearly composite. There's a whole range of possible PDFs that would be consistent with this hypothesis. Okay? So if you ever see an inequality in a hypothesis, it's automatically composite because there's a range of values that parameters could take. Some are trickier. This is just an equal sign, but I haven't completely determined the parameters because this type of probability distribution takes two data inputs. The mean and the variance. I've only given you the mean. Okay? All right? Is that all the vocabulary I wanted to discuss? Yes, it is. Okay. Let's look for 1 minute at this Nature article. Now that we have all these words back in our head.
What about statistical power?
Yes, power. Thank you. That was the last word. I wrote it and I didn't finish. I didn't finish writing. How do I find this thing? What are we? 481. Good. No, that didn't work. Statistics. Syllabus. Nature article. Read this. Okay, so let's look at it together. I'll let you read everything, but here's what people are literally doing. I do not know how these people can call themselves. If number theorists made this kind of mistake, we would just be fired. We should be fired immediately. Here's what happens. One study says, here is the mean, and here is our confidence interval from the null hypothesis. That is significant. The next study says, we reran your study, we got another mean, and this was our confidence interval. Therefore, we accept the null hypothesis, and this overturns the earlier study, which rejected the null hypothesis. The earlier study found significance, we find non-significance. No, you don't find anything. You can't reject the null hypothesis. That doesn't mean you've learned anything. Okay? Do you guys see the difference between this study overturns the earlier study, which found significance? They have the same mean. Your study just wasn't good enough. Figure out a better interval if you can really show that that it's not this, but you're getting the same means. You're seeing significance. You just can't conclude that it's actually significant because your confidence interval is too wide. Do you see what's how can this be happening in professional science? And yet it is. And it's actually prevalent, right? It's because people are learning procedures for how to evaluate statistical tests without ever learning what you guys are learning, hopefully, the underlying theory as to why these procedures became common practice. Does everyone see what happened here? It's just it's mind-boggling to me that this is allowed. Another point, a very valid point that they make, is, I don't see if it's, yeah, okay, so here's a bunch of journals, things getting interpreted correctly or incorrectly. We'll talk about p-values a little bit later, but here's another thing. Who said 0.05 is the best p-value? 0.05 has been the best p-value for like 200 years. Bless you. 200 years ago, there were, 10 labs on the planet that would study one question. Today, there's 1,000. If there's an actually interesting question, there are going to be 1,000 labs in the country that are going to study this question. They all set their p-value to 0.05. How many of them are going to get significance when there actually isn't significance? Yes?
Well, don't you have to also divide by or number of variables?
So we haven't talked about what the p-value is, but let's just say,
They shouldn't be doing 0.05 to begin with, because they're not taking the variables into account.
well, okay, so I didn't actually read this part. Is that what this part of the discussion is? I thought this part of the discussion was just people historically have chosen 0.05 as the right threshold. But let's just assume a 5% error rate is whatever that means. Never mind, let's pretend that they're doing statistics properly. Hopefully they are. Obviously they're not interpreting it properly, but at least hopefully they're crunching the numbers properly, right? If you today set up a 0.05 error rate in your statistical significance, and it's a question that other people are going to ask and other people are going to run, and 1,000 labs run it, 50 labs find significance. That's massive reproduction. Those 50 labs are going to publish their papers saying, we found significance. Those 950 labs that didn't find significance are going to shrug and say, well, I didn't find anything, I can't write a paper. I'm going to move on to the next project. Then they say, oh, these 50 other guys did find significance. I guess I was wrong, I didn't see it, oh well. You see?
So we need to publish negative results?
We must make negative results broadly available.
Broadly available.
Okay, there should be, and people are doing this now, certainly in medicine, you can no longer do a trial, an FDA trial, without saying, this is what I'm going to do, and this is how I'm going to do it, before I ever touch an experiment.
Yeah.
Like, this will be the analysis, the Excel spreadsheet is uploaded before there's any data in it, with all the analysis there. And then depending on what the number comes out to, that's what it is. Dylan.
Don't they use p-values like 10 to the negative 4 now in a lot of places? Or like, I think genomes are 10 to the negative 6.
So some places are doing it better than others. Some places are doing it correctly. Yeah, I don't know what the right threshold is.
Right. I think it depends on how many like possible combinations there are. That's what you...
Yes. And the right. So the number of, you will want to, so p-value, this is really a very delicate thing. But you're absolutely right, the 10 to the minus 4. Okay, if you hit a p-value of 10 to the minus 4, now we're talking, right? Because unless there are 100,000 labs running this and 10 of them getting it right or whatever, then we have to change what our notion of significance is throughout time. And this article came out during winter break and spring break, and I just saw this thing and I said, I pray that none of my students will ever make this kind of analysis, right? You did the analysis, you got a wide confidence interval, you got the same mean. They both saw the mean move from the null hypothesis, right? And this one said, we found non-significance. No, you didn't. You didn't find anything. That's okay. That happens. That's science. That's experiment. These guys found something. You didn't find anything. That doesn't mean that you have negated their study. Okay? All right. I want to make sure that point is very clear because apparently it's not to lots of people to do this for a living. Let's go back to our .cam. Okay, so I didn't write the word here. As soon as we're back. All right, so beta, the size of this type 2 error, so 1 minus beta, is called the power of the function. The power of the test. The power of the test. Why 1 minus? Well, it could have been negative beta. I mean, it's just something that goes up as beta goes down. Okay? Any questions? So that was that's all the words that we introduced last time. What a hypothesis is, null hypothesis, alternative hypothesis, critical region, type 1 error, type 2 error, level of significance, the size of a critical region, and the power of a test, and simple versus composite hypotheses. So the concepts are all trivial for you guys that can do hard calculations. There's nothing deep here. The words are new words, and we're going to get used to them by using them over and over. All right. So here's what I want to discuss today. Suppose you're going to test, so we want to test a null hypothesis against an alternative hypothesis. And we chose this critical region to be a function of x bar. In fact, basically everything that we've seen so far has been a function of x bar. Why x bar? There are other estimators for that same parameter. So let's see, for example, we want to find mu, want an estimator for mu from two trials, x1, x2, n equals 2. Just so that we can see what the critical region literally looks like in space. Okay? These are real valued random variables. So one thing we can do is we can look at x bar. X bar is a half x1 plus x2. And of course, the expected value of x bar is mu. And maybe a critical region, so maybe our critical region, I don't know, our critical region is that x bar is bigger than some constant. So what does that actually look like in space? So here's the space of all possible outcomes. This is R2. x1 has some value, x2 has some value. And what is the region x bar is bigger than k? Well, it's this thing being bigger than k, right? And so what does that look like? So what's the graph of the boundary? The boundary of the critical region is that x1 plus x2 is equal to, I'll bring the 2 to the other side, 2k. I mean, it doesn't matter what k is. Does everybody see that? If I'm averaging them, and I want to know when is it bigger than k, that's adding them and saying when is it bigger than 2k, and the boundary of that is when is it equal to 2k. So in other words, if x2 is equal to 0 on the y-axis, when x2 is equal to 0, so now I'm on the x-axis, that's equal to 2k. This is obviously a line, it's a linear equation. So here's 2k, and when x1 is equal to 0, x2 is equal to the same k, so here's that boundary, and I want to be above that boundary. Okay, that's the critical region. And that's how we're choosing to test this hypothesis. Why? Well, it looks nice. It kind of averages things out. Here's another way to test the same hypothesis. Okay, here's another estimator. Here's another critical region, C1. Instead of testing, slide this down. Good. Instead of estimating mu by the average, I'm going to estimate mu by twice x1 minus x2. What's the expected value of twice x1 minus x2? Mu. The expected value of this is mu. It's 2 mu minus mu. The expected value of this is also mu. So this is also an estimator for mu, and I could just as well test if this is bigger than k as my critical region. What does that look like as a region in space? Okay, here's my x1 outcome, here's my x2 outcome. So what does the boundary of this look like? It's when this thing is equal to 2k. So when x2 is equal to 0 on the x-axis, when x2 is equal to 0, I have 2x1 is equal to k. So x1 is k over 2. That's some point here, k over 2. Doesn't really matter what the point is. I'm just looking at the shape. How about when x1 is equal to 0? Then x2 is equal to negative k. When x1 is equal to 0, x2 is equal to negative k. Okay? So those are 2 points. That's the boundary of C. And I'll let you work out that I need to be bigger than here, so I need to be here. This is the critical region. Completely different critical regions. They're both testing, and if I choose k appropriately, these will both have the same size. And we know how to do this. right? This is what we did last time. Last time, we chose k so that the size, the level of significance, alpha, the size came out to alpha, right? This is the probability of C1, or C or C1, given that H0 is true. This is the type 1 error. We're in the critical region. We're not in the bulk. The bulk is here. This is what the tail looks like in these two versions. No, you don't like it. What? Tell me your name again. Yeah?
Gianna.
Gianna? Okay, you also don't like it?
Oh, no, I know you're looking at me. Sorry.
It's okay, but is this okay?
Yeah.
You're following me? I saw some, you had your brow furrowed. No, it's okay? You're too shy to say you don't understand something?
No.
Who isn't following everything that I'm saying right now? Thank you, Amelia. Go ahead, Yasa.
Just
And,
the notation,
the notation.
with the colon, I mean the semicolon.
The semicolon. Yeah, so last time I wrote it like this. It's the probability that we're in the critical region and H0 is true.
Oh, okay. It's just
Okay? And that looks a little misleading because it looks like what's the probability distribution of theta? No, I'm not saying theta has a probability distribution. I'm saying theta determines what the density, what the PDF is. And then given that PDF, what's the size of the critical region?
So why don't you just do a bar?
Yeah, bar.
I could do a bar, okay. So different people have different notation. I will conform to, I'm happy to conform to whatever notation makes you guys.
What are you conditioned?
It's conditioned, well, it's not really conditioned because it's not a random variable.
Okay.
So it's the probability, assuming that H0 is the density, what is the, but H0 being or not being the density is not a random variable.
Right.
It's a truth
Well,
that we're assuming, or we're assuming it's not true.
It could be like 0, 1. Like, true or false.
Yes, we can, it's just notation, right? Hopefully it's clear what this means. It means when you're computing this, you put in the PDF that H0 tells you to put in. And that's how you measure the size of this. Do you guys sort of have a picture? So you have x1 and x2, right? There's a density function. There's a surface above this plane, which is the density function corresponding to what the, locally in a neighborhood of this point, what's the probability that you land near this point? That's what that density function is measuring. And so once I have my critical region, what I'm saying is the integral, the area under that density function in the critical region is alpha. The integral in the critical region is alpha. Usually we just go straight to the variable x bar, right? Because x bar is itself Gaussian if the xi's are Gaussian. But now we're just talking completely in general terms. I don't know what this curve looks like, this surface, but I'm going to measure this region, and we've chosen k so that this region has size alpha. We've also chosen k, possibly a different value of k, so that that region has size alpha. The tails, I don't know what the tail looks like. That's what I'm saying. Right? What's the shape? What shape of estimator do we want to choose? We have a lot of flexibility. There's lots of different, right? You could take any linear combination whose expected value adds up to mu. Could you take x1 times x2 square root? If they're independent, is the expected value of square root of x1 equal to square root of mu? Is the expected value of x1 squared equal to mu squared? No, right? So you can't, so let's keep it linear, okay? There are all kinds of subtleties happening, but let's just keep it linear. Any linear combination, 100x1 minus 99x2 is another thing that has expected value mu, and that's some other region, right? We have lots of regions, and for any region we can choose a value of k far enough so that the tail, the integral of this surface, in this region has value alpha. Ernst.
You wouldn't ever do that, right? Because the variance is like a lot higher if you do it any other way than x bar.
That's what we're about to prove. What we're about to prove, so it's not the variance, it's the power. Once we've determined the size of a test, right? This is our 5% confidence that we haven't made a type 1 error. Now let's make sure, so which of these regions is best in terms of the power? That's the Neyman-Pearson lemma, okay? So what we want to say now, which of these regions is most powerful now notice, at the moment we are discussing nothing but H0 and the critical region. H1 hasn't come in at all yet. But if we want to evaluate the statistical test, we want to know its size and we want to know its power. So which of these regions is most powerful for H1? For testing H1. In other words, has the lowest probability of also making a type 2 error. We've calibrated the values of k so that the type 1 errors are the same. They're the same statistical tests from the point of view of size. Now we want to see, given an H1, which of these is the better region? What's the most powerful region? Okay? Is the question clear? Don't tell me. Tell me. Tahina.
So the power, like, does the power change depending on like what the changes?
Yes, because H1 is going to say, instead of the original curve, so H0 determines what the surface, what the density looks like that we're integrating over, but we've calibrated k so that both of these have integral alpha when integrated with the likelihood of H0, with the PDF of H0. H1 is a new PDF. It says, no, they're not distributed like H0 says, they're distributed like H1 says. So there's some new surface here, and there's a new surface there, and who's to say that these two integrals are the same? One of them will be smaller than the other, in general. That'll be the better test. The one with the smaller integral is the more powerful because power is 1 minus the probability of a type 2 error. Did that answer your question? Other questions?
Make a circle.
Can you make a circle? Sure. You mean can the region be like everything outside of there? Yeah. Will that be a region that tests mu? I don't know, right? We want something that's an estimator for mu. But maybe, right? Okay, what's that?
Not
No, it's about mix or both.
Uh-huh, okay. Okay, so here's what you're gonna do. How do you figure out what the integrals are of these things? Remember what the likelihood function is? Recall the likelihood L, let's call this L0. Well, let's call this the likelihood of a particular outcome, x1 through xn, given the hypothesis H0. What does that mean? So we'll abbreviate this to L0. It's just the density above a particular point. So here's x1 through xn in the plane. The likelihood is, assuming H0 is true, what's the density at that point? In other words, this is, so L0 is the product. So it's fx of x1, assuming H0, times fx2 times fxn, assuming H0. Okay, let's see this explicitly. H0 says that your variables are IID Gaussian, are normal with mean mu0, and let's say variance 1. Okay? What is the likelihood of x1 being equal to some value x1 through xn being equal to some value xn? Mona, something?
Sorry, what? No.
Oh, okay. Unrelated.
I just asked, is that a 1 or a comma? But it's a comma.
Is that a 1 or a comma? That's a comma. Maybe I should make it a semicolon.
I'm also really sorry.
It's hot. It's hot. It's
I'm also
Friday.
really sleepy, too.
Yeah. Sorry. We're almost there. I have to prove a lemma, and then we.
You can write a subscript for the x's.
I don't have to write a subscript for the x's.
You
Yeah.
know?
I could just write f sub h0 or f0, right? I worry that the more I abbreviate,
I mean, they all have the same distribution, so it should just be x.
Well, but it's x depending on what h0 is, because in a second we're going to have a new likelihood, which is the likelihood that h1 gives. Right? So I do want the distinction between 0 and 1. So I'm putting all of the abbreviations into L.
I mean, like, you don't need like x1 semicolon h0. Like just
Oh, this is not x1, yeah, that's right, they're all the same. So these are all x. They all have whatever the distribution is fx, but it's fx
yeah.
with h0 as the law. So what would this be? Does everybody know?
1 over square root 2
Yep.
pi.
So the first one is 1 over root 2 pi e to the minus x1 minus mu 0 squared over 2 and sigma squared is 1. So that's just the first value. And then there's a second value, and then there's a third value, and then there's an nth value, which is 1 over root 2 pi e to the minus xn minus mu 0 squared over 2. Okay? So that's the likelihood of this outcome given h0, given that we're assuming its variance is 1 and mean is mu 0. Okay? And similarly, there's an L, so this was L0. And L1, if L1 says that the xi are normal with mean mu1 and variance L1, then that likelihood, so then, if that's H1, hypothesis 1 is this, then L1 is equal to the same thing except with mu1s instead of mu 0s. These are two different functions. Okay. So now we're ready for a theorem, well, lemma. So this is called the Neyman-Pearson lemma. The lemma says the following. Suppose your critical region has the following property, is such that L0 of the outcome divided by L1 of the outcome is at least some constant for all x in the critical region, and L0 divided by L1 is at most that same constant for all x outside the critical region. So if this ratio of the likelihood of h0 to the likelihood of h1 is at least something in the critical region, and at most that same thing outside the critical region, then that critical region is a most powerful critical region. Then C is a most powerful critical region for testing h0 against h1. Let's see this in action before we prove the lemma. Let's see what it means. Okay? So we're trying to construct, let's go back to this example. So using this lemma, let's construct a most powerful critical region. Okay, we'll see what this means in a second. Yes?
Does the C 0 mean the interior?
The complement.
Oh, the complement.
So this is complement. This is omega take away C. I would write C for complement, but I already have a C. So some people use C0 for complement. Some people use C twiddle for complement. I don't know. Do you have a favorite notation for complement?
C.
C to the C.
See, that's the same.
All right, C to the C. You don't mind it? I don't mind it.
Because C to 0 I thought was the
Well, it's interior in topology, yes. Did I use that before? Somewhere else I have C0. C0. CC. Okay, you don't mind C to the C? I'll keep C to the C. C to the C complement. Okay? In other words, you all know what I mean by C complement. This is C, this is C complement. Right? Everything that's not in C. Okay, let's go back to this exercise. there's our example. So, we want to construct a most powerful critical region to test hypothesis 0 against hypothesis 1 in the case of this normal. Bless you. The hypothesis 0 is that the mean is mu0. The hypothesis 1 is that the mean is mu1. We're assuming that the standard deviation is 1. Okay? So what do? The Neyman-Pearson lemma says take this ratio. So look at, let's go here, look at L0 divided by L1. Bless you. So what will happen when we look at L0 divided by L1? They're basically, the constants, these root 2 pi's, cancel.
Yeah, cancel.
Right? There's one here, there's one there. I'm taking the ratio of these two things. So what I get is e to the minus x0 minus x1 minus mu0 squared over 2. That's what I get on top, and there's n of them, xn minus mu0 squared over 2. On the bottom, I get e to the minus x1 minus mu1 squared over 2, all the way out to e to the minus xn minus mu1 squared over 2. I'm waiting.
Wait, in the numerator, sorry, so in the first term's exponent, what is that subscript for x?
It's 1.
Oh.
So there's x1 through xn, but hypothesis 0, the null hypothesis, is that the mean is mu0. The alternative hypothesis is that the mean is mu1. That's the only difference in this ratio. Julia?
Are the x's identical here?
Identical.
So we could write it as e to the negative n. Oh wait, no, these are added up.
They're added up, but there's a square here.
Oh.
We have a little bit of algebra to do. We have a little bit of algebra to do to see what's going to happen. Okay, so let's do that little bit of algebra. Slide this up. So what is the algebra? Well, all right, let's just do it. So e to the minus, there's a 1/2 everywhere. And then what's left over? So I have x1 minus mu0 squared. That's x1 squared minus 2x1 mu0 plus mu0 squared. That's the first bit. That's this bit. Then there's a second one. x2 squared minus 2x2 mu0 squared. Plus mu0 squared. All the way out to the last term, which is xn squared minus 2xn mu0 plus mu0 squared. Is everybody happy with this being the numerator? Then there's a denominator. But before we get to the denominator, does everyone see that this is x1 minus mu0 quantity squared? I pulled the 1/2 all the way outside, I pulled the minus sign all the way outside. Product of e to the things is e to the sum of the things. So far so good? Mona, it's good?
Yep.
All right. What goes on the bottom? Exactly the same thing, except with instead of mu0s, I have mu1s. x1 squared minus 2x1 mu1 plus mu1 squared. x2 squared minus 2x2 mu1 plus mu1 squared. All the way out to xn squared minus 2xn mu1 plus mu1 squared. Okay? Does everybody agree with that? Okay. I have an e to the minus half x1 squared on top, e to the minus half x1 squared on bottom. Those cancel. Do these cancel?
No.
Nope. Do these cancel? Nope. Do these cancel? Yep. Nope. Nope. How about xn squared on top and bottom? Right? Everybody see that? So what's left over is e to the minus a half. Now let's group these terms. I have a minus 2 x1 mu 0. And in the bottom, there's another minus 2, so that's a plus 2 x1 mu 1. That's grouping this term and this term. Let's get the same thing with x2s. Minus 2 x2 mu 0 plus 2 x2 mu 1. See what I did there? Minus 2x2 mu 0, that was that term, plus 2x2 mu 1, that was this term that was in the denominator. All the way out to minus 2 xn mu 0 minus mu 1. We're not done. There's an extra bit. That was only taking these terms into account. And what's left over is a mu 0 squared plus a mu 0 squared plus a mu 0 squared plus a mu, n of these mu 0 squared. So that's n mu 0 squared. And in the bottom, I have a mu 1 squared and a mu 1 squared and a mu 1 squared. So that's minus n mu 1 squared. That is the ratio of the two likelihoods. Does that make sense? Kiana.
They're being multiplied?
They're being multiplied. That dot is meant to be multiple times. Ah, that looks like an X. Times. Is that better? It's the same thing. Yeah, I didn't change it. It's multiplied.
The second term is from where?
The second term is that I didn't take into account that mu 0 squared in the numerator and that mu 1 squared in the denominator, and there are n of them. In this line, I only took out the terms that had x's in them. This does not have any x's in them, so it's a constant. No matter what critical region you're going to choose, this thing is just going to be a constant because it only depends on h0 and h1, which have been fixed. So let's simplify this a little bit. So we have this constant in front. Let me write it just so that you don't get confused. That constant's still there. And now let's look at this. So we can kill the minus signs and the 2's, actually. But everybody has a mu 0 minus mu 1 in it. And then what's left over? So here, the minus signs have been canceled. The 2's have been canceled with the 1/2. What's left over, I've pulled out a mu 0 minus mu 1 everywhere. What's left over is an xn and an x2. And well, I didn't simplify this. I did, but it has the same shape. What's left over is an x1. Does everybody see that? In other words, this is more junk. This is just some constant. There are no x's in it. No xi's. And what is this? It's e to the mu 0 minus mu 1 times n times x bar. X bar is the average. You take the sum and divide by n, but I didn't divide by n, so let me multiply by n so that right? And x bar is the sum of the things instead of the average of it.
Can you just say what you said before? You said all that stuff with the star.
So this is a term, but that term doesn't depend on the x's at all.
Okay, yeah.
So no matter what critical region you choose to look at this test,
It's like a constant.
it's the same, yeah, it doesn't at all depend on the actual location. Do you want to take this kind of region or that kind of region?
Okay. Thank you.
Yeah. Juliet.
What does it say inside the parentheses?
No xi's. So this is a constant. No xi's, just constant. Just constant. Okay, that's this thing. And then the only way that this depends, so if you want to have, let's look back at this lemma. The lemma says, you look at the ratio of the likelihoods, if your critical region is exactly the place where the ratio goes from being positive to negative, that will be the most powerful critical region. So among all critical regions which have the same size, maybe I didn't say that, suppose C has size alpha. Okay? First, so you have your hypothesis, H0, your null hypothesis. You can have a ton of critical regions that have the same size. Right? That's what we saw before. All these different places you could try to capture this critical region. The one that will be the most powerful among all those critical regions of size alpha is the one which captures this switch in likelihoods from being above k to being below k once you leave the critical region. Okay? Look at this ratio of likelihoods in our example. It is a function purely of x bar. So the only way you're going to flip the only region that will be a most powerful critical region is the region that flips according to the value of x bar. Let me write that down. So the ratio of likelihoods is a function, is a monotonic function of x bar. So if L0 over L1 is less than some constant inside C, and L0 over L1 is bigger than that same constant outside C, the only way that happens...
Wait, isn't that the opposite of what we just said?
Yes, sorry. Thank you. I have the inequalities the wrong way.
Well, the book does them that way, but it doesn't matter, right? As long as
It doesn't matter, yeah. Whichever...
As long as-
You're capturing the
Yeah,
transition.
yeah.
Which way do I want to say it? I mean, which way is the actual lemma? Did I get it wrong the first time? Yeah, I want the ratio of these likelihoods exactly.
Yeah, the book says it's right.
Sorry.
Swap.
Sorry. I said it right the second time, but not the first. Let's think about why it must be this, right? If this region is supposed to be a good region, a powerful region, then the likelihood of the null hypothesis divided by the likelihood of the alternative hypothesis should be small. The null hypothesis should rarely happen in this region, and the alternative hypothesis should happen a lot in that region. And that should be exactly the transition. Thank you, Cindy. So this ratio being less than k inside C and this ratio being bigger than k inside C, the only way I can change that, the only way I can have exactly that on-off switch is by adjusting the value of x bar. So if this is true, then C has the shape x bar is bigger than some other constant. So the most powerful way to test whether mu is above or below some value, in the case of this Gaussian, is to test whether x bar is bigger than that value. Not whether twice x1 minus x2. That will not give you that can't possibly give you a more powerful test than this test, which checks the mean. So we were right to be checking the mean all along, but this proves that we were right to be checking the mean all along. All right, let me give you a proof in our remaining 6 minutes of this lemma. Is this okay? You guys see? I'll leave the lemma up so we can stare at it. The proof is extremely simple, which is why it's a lemma. So let's talk about it. Okay. So proof of the lemma. All right. So we have a region C. Suppose C is such that L0 over L1 is at most k in C, and L0 over L1 is at least k in C complement. Let D be another region, critical region of size alpha. What does that mean? It's a critical region of size alpha. What does it mean for C to be a critical region of size alpha? i.e., if I integrate all the possible outcomes in C, its size is alpha. C is where we reject the null hypothesis. This integral needs to come out to alpha. And what will I be integrating? I'll be integrating the product of the densities, assuming that H0 is true. Well, if H0 is true, the product of the densities, that's literally what L0 is measuring. L0 is the product of the densities of the outcomes, assuming hypothesis 0 is true. And I integrate that over C, that's literally the size of the test, and I'm assuming the size of the test is alpha. Does everybody see that? Taking it. We're assuming that D is some other region, so let's draw this picture. So C in our example is this, and D in our example is this. D is some other region which also has size alpha. In other words, the same integral, now over D, with the same likelihood, also comes out to alpha. Does that make sense?
My question is,
Are we assuming D is
are we assuming independence?
between C and D? The independence of what? Independence of the Xi's?
Yeah.
Yes, the Xi's are still independent for this example. In fact, it's true more generally, as you'll see in a second, but never mind. Let's say in this example. For everything that we're going to be doing there, they will be independent. But it actually doesn't matter, whatever the likelihoods are. You'll see from the proof what comes out. Okay? So this is just because of independence, let's say they are independent, in which case the likelihood function is just the product of the individual likelihoods of taking on that value, assuming that our distribution is whatever the null hypothesis says. And that's the same for D. Okay? Now, let me draw these two regions as kind of a bubble. So here's a set of all possible outcomes. Here are the outcomes in C. Here are the outcomes in D. You see they have some regions in common. Let's write this integral as an integral over the regions in C intersect D of L0 plus the integral over the regions in C intersect the complement of D of L0. If I take C union D and C, you want a C there for complement. Right? These two things sum to the total integral over C of L0. In other words, I'm integrating over this piece of C, and then I integrate over this piece of C, L0. That's the same as integrating over all of C of L0. Does that make sense? But the same thing is true for D. If I integrate over all of D, I can integrate over D intersect C, and I can integrate over D intersect the complement of C. Right? I'm just breaking the integral according to whether or not you're in C or outside of C, and I keep putting zeros instead of the C's that you guys want to see. The C's that you guys want to see. It reads better than it sounds. All right, so far so good? But D, the integral of L0 over the intersection is the same on both sides. So what I've shown is that the integral of C outside of D is the same as the integral of D outside of C. I'm just going to cancel this and this on both sides. This tells me that the integral of L0 on C intersect D complement is the same as the integral of L0 on D intersect C complement. In other words, the integral over this bit of this region is the same as the integral over this region, where we're in D but not in C. Does everybody see that? Let me go a little fast in the interest of time, and we can do it again on Tuesday. Review the argument. Okay, we're in C. So what's the ratio? Our assumption is that inside C, you can almost see it. Our assumption is that inside C, L0 is bounded above by some constant times L1. So if we're inside C, inside C, L0 is bounded above by some constant times L1. So I'm going to replace L0 here. So this whole integral is bounded, these two things are equal. It's bounded above by some constant times the integral over the same thing of L1. That's because inside C, I can replace L0 by KL1, and that makes everything bigger. On the other hand, if we're outside C, this is outside C. Outside C. So, when we're outside C, the ratio goes the other way. Then L0 is bigger than that same constant times L1. So a lower bound for this integral, a lower bound is the integral over D intersect C complement of the same constant L1. It's a little trick. It's a tiny little trick. Let me write this down again. This means that this constant times the integral over L1 D intersect C complement is a lower bound for the integral over the same constant, the same L1, C intersect D complement. We're going to do this more slowly. I just want to get to the end. We're almost there. I can cancel the constant on both sides. So the integral over D intersect C, this is D intersect C complement. This is C intersect D complement. The integral of over L1, so if I integrate L1 on this region, I get something that's smaller than if I integrate L1 on that region. Now let me add to both sides the integral of L1 of D intersect C and the integral of L1 of D intersect C. What do I get here? It's the integral, that's an L1, it's the integral of L1. I have D intersect C and D intersect C complement. These two together make the integral over D. That's a lower bound for, what do I get here? It's an integral of L1 on C intersect D complement and C intersect D. That's the integral on C. Right? Everybody see that? And so, what are we measuring? These are the sizes. This is the power of the function. C has a bigger power than D. Okay? Something happened. All right, I'm going to have to come back to this. We got the inequality the wrong way around. This is the error. The error on C1 is supposed to be better than the error on C2. There's a mistake here. I'm out of time. I'm rushing it. We'll do it again on Tuesday and get it right. And there's homework due next Friday.